All right, it's recording. Let's begin. Shh. Thanks, team. Have a pen, pencil ready. All right, so you should all have a sheet. Today's exercise 4E and 4F. What we're looking at today is just looking at some properties of odd and even functions, and you'll start to see there's some patterns. And ideally is that once you see the patterns, you should be able to sketch roughly that graph. Okay, that's polynomial. All right, so it's just looking at certain properties to note so that when you get something like that, you can identify key points. Now let's have a look over here. Tip, look for the number of, and I'm going to write here, x intercepts an equation has. And often you can tell the number of x intercepts based on the number of linear factors. Right? So when you have a quadratic equation, for example, x squared plus 2x plus 1, and if you factorize that, that's what? X plus 1 and x plus 1, right? Same thing. So that factor, that normally tells you, if you use null factor law, it tells you where it crosses the x-axis. That's your x-intercept. So the number of linear factors that you have tells you how many times it crosses. But what's interesting is that as you go through, you start to notice there is, thanks team, there is something special when you have a square and you have a cubed on a factor. Let's have a look here. When you have a quadratic factor, the graph has a turning point. And when there's a cubic factor, the graph has an inflection point. This is an example of a quadratic graph, x squared. You have a turning point right here at 0, 0. This is a odd power, which we have an x cubed cubic graph. It also has a point called the inflection point. Inflection point just basically means that the graph goes from one sign, so concavity, so it concaves up, and then it changes sign and it concaves down. Okay, that's the only difference. Or if it helps you, please don't speak while I'm speaking. Wait till I finish and then you can speak. As I was saying, the other way is that you can think of it as find the double derivative. If you find the double derivative where it's equal to 0, that essentially the change in sign, so in the rate of change, that's where you know there's an inflection point. Okay, but that's for later on. Right now I'm just telling you where there's an x cubed, this is what the graph looks like, and then where there's a square, it turns back up, right? And when it's linear, so notice here this is a linear factor, we know it crosses through. So if I gave you an example where I said x minus 1 and x minus 2, you expect that at 1 and 2, the graph crosses through 1 and it also crosses through 2. That linear factor means cross. And what we see in patterns with x squared, which is interesting, is that there's always a turning point. So it goes back up. Rather than cross through, it goes back up. And then in cubics, it has that concavity or that inflection point look. So as you can see, as I increase the powers, I go from x squared to x to the power of 4, okay? And this is x cubed, this is x to the power of 7, asymmetrical versus symmetrical. The only difference between a square and an x to the power of 4 is between -1 and 1, it gets flatter. Okay, so it gets flatter between -1 and 1. And the reason for that is, again, fractional powers. The higher the power, the larger the denominator. The larger denominator, the smaller the value is. Okay, that's the idea. That's why it gets flatter between -1 and 1. But what I want you to take out of it is that, okay, well, we know this is a quartic graph over here. Because overall, that's an x squared. Overall, if you expanded the brackets, that would have been x squared. And then you're times it with another x squared. Well, together, it must be quartic. So in some ways, this is what we know about a quartic. A quartic graph should look like a quadratic. It's symmetrical. And if it's positive, it goes up infinitely. This is still the same. If you expand the brackets, the first thing I can tell is that the square of x gives me positive x squared. The square of x is also positive x squared. And if I times the 2, I'm going to get a positive quartic graph. So I know that in the long term, it should go up. It should go up for both of them. Okay? But what changes from the first one x to the power 4 here, and then down here is still a quartic graph, is that this has two, not linear factors, but two quadratic factors. So you can see here, I'm going to delete this now. These two here are quadratic factors. So we said a linear crosses through a quadratic factor, meaning there's a power of 2 to it, it curves back up. And can you see that at x minus 1, which normally the x-intercept should be at 1, so here's 1, there's a curve. Here, x-intercept normally is at negative 2, and again, when you have a repeated factor or a quadratic factor there, it repeats or turns back a negative 2. How do we know that it goes both up in that direction and looks like a W? Because, again, we know that overall a quartic graph should look like this. But if it has to have two x-intercepts, the only way to draw this shape and touch negative 2 and 1 was a W shape. Okay, and then same thing if you wanted a negative, you could have the M shape. We could have gone like that. Okay, so you put a negative to it. Now, that means I can play around a couple of things, and you guys can have a prediction of what this looks soon. That means I can give you a random number of factors, and depending on what type of factors I give you, whether it's even or odd powered, you can predict what the graph should look like. So if I gave you something like this, x minus 1, so I want it to cross through at x equals 1. Then I say at x minus 2, I want it to do a bit of a turn back up. Okay, so it has a turning point. And then maybe at x minus 3, I want it to have an inflection point. So what does that look like? Let's have a look at the overall power. What kind of function do I have? This is an x to the power of 1. This will end up being an x squared. This will be an x cubed. So if I multiply them all together, what type of function am I going to get? Odd or even? Even, because 1 plus the 2 plus the 3 gives me 6, so x to the power of 6. So we know an x to the power of 6 should look like a quadratic. The only difference is the base should be quite flat. But there are three numbers I need to work out. On the x-axis intercept, if I were to predict what this graph looks like, which I haven't seen yet, but if I were to predict it, I chose 1, I chose 2, and I chose 3. I wanted it to, again, you have to draw this shape, but it has to cross through 1. It has to has a turning point at 2, and then it has to have an inflection point at 3. If you try to do a bit of problem solving right now, you can probably picture what it looks like. See, the only way for it to turn at 2 was as soon as I come to 2, I have to turn it back. And then the only way to have an inflection point at 3 and still maintain that I keep going up and I keep going up on either side, it's likely the shape will look something like this. Okay, so let's try it. Let's try on Desmos. I'm going to go into Desmos right now. So this is an x to the power of 6 graph with one linear factor, one quadratic factor, and one cubic factor. Let's see what it looks like. So I'll go to Desmos. Let's type in Desmos. So here we go. I'll delete this. I was working with my year 11s today. Y equals, I said, I wanted to cross through x minus 1. So it crosses through 1. I wanted to cross through 2, but I wanted to have a turning point, right? But then I said I also want at 3 an inflection point. Can you see the pattern that we were able to describe? That overall, this is an x to the power of 6. But what's happening in between is at 2, it had to touch it because I put a square. Then I want an inflection point at 3. That's exactly what's happening. That's my cubic inflection. And it goes up because I know it's a positive x to the power of 6. Had I known it was a negative, then I know it has to go down, then I would have to draw it the other way around so that it crosses through 1, turning point at 2, inflection point at 3. This is all they want you to understand from E and F. They want you to understand that there's an odd power, there's an even power, both of which they have some properties that we can deal with. So whether it's x to the power 7, 9, 11, you can predict what it should look like. So, your sheet now, I want you to have a look at the question I gave for you. What would this one look like? Have a prediction, draw it on your sheet, and then we'll test on Desmos to see if you're right. I'm going to pause it. Let's see what you guys got. So, first thing is you got to figure out, listening, eyes and ears towards the board. First thing you got to figure out is it an x to the power 7, 8, 9, 10? What is it, odd or even? So we'll start off. This is clearly linear, so it's x. That's still x. This is going to be an x cubed. This is going to be an x squared. Notice there's no negatives as a coefficient of x, so likely it's going to be a positive x times x cubed times that. So that's x to the power of 7. Oh, thank you. So I know it's an x to the power of 7. So you should expect it to look, and because it's positive, it should be, as you go infinitely left or right, it should go up infinitely and it should go down infinitely. So your shape, if you've drawn it now, as you go negative, it should go all the way down, and if you go to the right, it should go all the way up. If you haven't got that, you've got the wrong shape, okay? Second one, we look at the intercepts. X plus 1 as a factor implies that negative 1 is an intercept. X minus 2 tells me it should have a 2 involved. It should also have a 1 involved, and it should also have a negative 3 involved. So these are 3 points that you should be looking at. The linear ones, it should cross through. So it should cross through at negative 1. So cross, through 2, inflection point at 1, and then a turning point at 3. Okay, now we just don't know where the shape is. So you start from left to right. Remember, at the end, it should be going up, and at the start, it should be going down. That's how it should start, right? So I would predict that it goes through negative, oh, sorry, not negative 3. Was it? At negative 3, it should be a turning point. So it must be a turning point. And it has to go through negative 1, so it means it must cross through. And at positive 1, it has to have an inflection point. So the only way to have that inflection point and then still cross through 2, there must be something like this for it to cross through 2. And that's it. It goes back up. So I'm predicting this is what the shape of the graph should look like. Let's see it on Desmos. What did I get? Yeah. All right, so infinitely down. Turning point at 3, crosses through negative 1, inflection point at 1, and then crosses through 2. Gives you a general idea of what it looks like. This will help you, this skill, if you're able to pick up on that pattern, that will help you do this one, which you should be able to do now without a sign diagram. For those who didn't understand what I said, then this is where a sign diagram has its place. The other times that you use a sign diagram, thank you team, the other time that you use a sign diagram is if the question asks you to justify your reasoning. So there'll be questions in the exam where they'll say, state the maximum or absolute value, and then justify your response. You actually have to then prove how you knew a certain value is the maximum. So after you find the derivatives and you sub in the endpoints, a sign diagram is how you show it. But if I were to draw it, I simply look at this and I'll sketch it. Now, if you were to have a look at this one, there's a key difference between this example and then the other ones I just gave to you. What's one obvious thing or one hidden thing that I chucked in? Does anyone see it? Oh yeah, I see what you mean. Yes, that's correct. That little negative there. So whilst this is still linear, so yes, it's an x. This is also an x and this is an x, but notice this is a negative x. So if you multiply it, it is a cubic, but it's a negative x cubed. So it should be asymmetrical, but as you go on the left, it goes up, and as you go to the right, it should go down. So this shape still crosses through negative 1, still crosses through 3, and still crosses through 5, but you have to make sure that it has that shape that it goes. As more negative you go, it goes up. The more positive you go, the further negative it goes down. So that, if I were to sketch it, I already have a prediction of what it looks like. But if this question was to ask me, like to justify my answers, then you have to use a sign diagram. Now, I'm assuming all of you know how to use a sign diagram? Yes, no? No? Okay. Sign diagram. Essentially, you split up your intervals. So we had our 1. Sorry, should that be a negative 1? That might have been, yeah, that should be a negative 1 there, sorry. Negative 1, just fill that in. This is meant to be a negative 1. So negative 1, 3, 5. Here's your negative 1, here's your 3, here's your 5. Those are the 3 key points. We know we cross through all 3. When you're using a sign diagram, we test literally every region. At negative 1, I expect it to be the x-intercept, so it should be 0, 0, 0. On your sign diagram, how do you represent a gradient of 0? Horizontal line. So it must be flat at that point. Okay? The other thing that we also know is that a -1, okay, so less than -1, so that means on the left side of the graph, so from -1 onwards, see, without the graph, how do you know that it's positive? The only way to prove that this is positive is if you chose any x value in this direction, so less than -1, and you have to sub it into the function. So if this is a justified question, you actually have to write it. Okay, what you can't do, and I see a lot of students do when it comes to the SAC, because you already know what the picture looks like, don't do this. Don't do positive, because you know it's going to be in the positive side for the y values. Don't just do 0, and then you know that it's going to be negative, 0. I know that you know this is positive. I know that you know that's 0. I know you know that's negative. But you actually have to write how you knew all those values. So that means if you're doing it in a SAC and they ask you to justify, here you actually have to pick a value. So you actually have to type in what f of, pick a value, -2. Evaluate it. Is it a negative or a positive? Here, we already know it's 0 because you can do null factor law. Here, you have to pick a value between -1 and 3 to prove that the y value will be below the x-axis, and it's going to be a negative y value. So you actually have to pick values. Okay, you can't just do the signs and then just go, yep, I've got the sign, I know what it looks like. That if I had the 0 line here, positives in this region, 0, negative region, positive, positive, negative. You can't do that. So this is positive and negative regions. That's what a sign diagram is. It gives you a picture of what the graph would look like. So if you're able to read what I was able to teach you and you're able to picture what the graph looks like, great. But if it asks you to justify, that means in these steps here, you actually have to pick a value and then test it. So you actually have to do f of, say, -2, work it out. So in our case, if I had a calculator, I would define the function. So let's do it all again. So define f of x is equal to, bracket, x plus 1, 3 minus x, and x plus 5, x minus 5. You actually have to work out what f of -2 is. It's 35. So now you can say, yes, positive value, positive sign. We already know this is 0 because that's f of -1, which you can prove to be 0. Here you have to pick a number that's between -1 and 3. So you might do 2 or 1 or 0. It's up to you. So if you do f of 0, that's probably the easiest one to do. So you type in again, f of 0. It's -15. Then you can say negative. So you can see it's plus 0, negative. But without this first line, without evaluating it, that will penalize you. If the question asks us to justify. So if it doesn't ask to justify, you can skip this whole thing and do what I just taught you before, analyze by understanding the graph. Okay, so that's the only thing I thought I'd add in. And that's what a sign diagram is. It essentially gives you a map of when it's 1, -1, 3, and 5. Is it in positive above when it's less than -1? Is it negative when it's between -1 and 3? Is it positive again when it's between 2 and 5? And those vertical lines are your zeros. So that's where it crosses the x-axis, and then you get a picture of what it looks like. Okay? Thanks, boys. So these are your y values. So you can see that's your positive region, negative region, 0, 0, positive, and then negative. That's what the sign diagram is. Okay, so what do you, boys? Thank you. That's exercise 4E and F. That's the essence of it. So if I had to sort of summarize it for you, it's a very short exercise. They really just want you to be able to read the pattern. So even versus odd, symmetrical versus asymmetrical, turning point versus inflection point. If you're able to do this and understood what I was saying, that's the essence of E and F. Okay, so you can practice those exercises or move on. If you've already got it, just move on. Yeah, just do a couple of questions, get a feel. If you haven't done a sign diagram before, practice a bit of that because that will be needed for justification. That's the only one that's in your study design that they will test if you know how to justify, or you can write it. Using a sign diagram is easier. Okay. Or if you know double derivatives, you can use that too. All right, I'll stop the video there.